Okay, I'm going to go through the homework on collisions. So, remembering our three types of collisions, we have elastic, where objects bounce off each other and they separate cleanly. There's no like one sticking to the other happening. And so, we've got this equation. We have our two masses before, then we've got a collision here at the equal sign, and then this is them after. So they both got generally different velocities after the collision. Then inelastic, we have two objects that start off separate. So it starts off the same way as elastic, but then they get stuck together. They combine somehow, depending on the collision. And so we end up with our combined mass moving at the same velocity together after. And then our exploding or our separation collision, where our objects start off together and then somehow they get separated from each other. So we've got one moving one way, one moving another. And so here they start off together at the same velocity and then they're separated. Okay. So we've got a couple of examples of each of these in the problem set. So let's see. So first problem, we've got a car going 23 meters per second and it rear ends another car going 17 meters per second and they're on ice. Okay. And they're going in the same direction and they stick together after they collide. So how fast do they move together immediately after the collision? So we see through a few keywords here. Stick together. How fast do they move together? That tells us that this is an inelastic collision. Okay, so this means the two objects, they started off separately and now they're stuck together. So we've got our two cars. Okay, this one's driving 23 meters per second. So this is my before picture. And both of my cars are driving along, and then this car is going to rear end this car. And so we end up with our two cars stuck together. These look like mushrooms with wheels, but that's okay. They're stuck together and they're both moving. Okay, they're both moving together after the collision. And we want to know how fast do they move immediately after the collision. We're looking for our final velocity. Okay, so we're going to use the inelastic collision equation here. M1 V1I plus M2 V2I equals M1 plus M2 times VF. So we've got our individual momentums of our two objects, and then after they're combined, we've got a combined mass. They're moving at the same velocity together, and we want to know what that is. We don't know that value. Okay. So writing out all of our little givens here is important. Let's see, M1 is 1,875. I'm just getting that from here. Kilograms. V1I is 23 meters per second. M2 is 1,025. M2I is 17. And then we're looking for VF. We don't know that. So let's fill these in the equation. We've got 1,875 times 23 plus 10,025 times 17 equals, let's go ahead and add up our masses. 1875 plus 1025 is 2,900. So 2,900 times VF, and we're solving for VF. So I'm going to simplify these out. I'm going to do 1,875 times 23. That's 43125 plus 1025 times 17. That's 17425 equals 2900 times VF. I'm going to add these two up. 17425 plus 43125 gives me 60550 equals 2900 VF. And this is all just math, right? I've figured out my givens, my scenario, which equation to use, and I'm just plugging things in so I can solve for VF. Okay. So I'm going to end up with 60550 divided by 2900 equals VF. Oops, I didn't mean to clear that. Gives me 20.9 meters per second. Okay. And we didn't have any direction change here. Like we've got a car driving, and then it says that it rear ends this car that's going in the same direction. So then they continue on in the same direction, glom together. Okay. Is kinetic energy conserved? We know that no, it is not conserved when we have an inelastic collision. Definitely with vehicles colliding, you're going to have some transformation of energy into like a thermal or a heat energy. So we can figure out our initial and our final kinetic energy. Our initial is just going to be 1/2 m1 v1 squared v1I squared plus 1/2 m2 v2I squared. That's my kinetic energy equation. I know my M1s and my V1s from up here, so I'm just going to do some math. 1/2 times mass times velocity squared. It's going to be a big number. 495,938. And then 1/2 times 1025 times 17 squared. 148,113. I'm going to add those two together. 495,938. So that's 644,051 joules that they had initially as kinetic energy. Okay. All right. And then my final, their masses will be combined. They're moving at this velocity that we calculated. So 1/2 times 2,900 was my combined mass when I added these two, times 20.9 squared gives me 1/2 times 2,900 times 20.9 squared equals 633,375. So we lost, or we transformed, let's see, 644,051 minus 633,375. We had almost 11,000 joules that transformed. So 10,676 joules transformed from KE to another type of energy. I mean, we don't know for sure what it is. It's likely a thermal. Some sound maybe because there was a loud crash. The point is that we not all of our kinetic energy was conserved. Some of our energy turned into something else. So, okay, so that is all I have room for in the first video. I may have to do one problem per video. That's okay.